Greetings, everybody. Let's have a look at subspaces of vector spaces, part 1. So suppose that we are given a vector space and they also give us a non-empty subset of V. Then in the case that W actually is a vector space on its own, then we say that W is going to be a subspace of V. And if you need to review some of the previous axioms that we had for a vector space, then I'll point you to a previous video. So we've got a theorem that says that if V is going to be a vector space and we've got a non-empty subset, then the only real criteria that we need to look at to see that if W is going to be a subspace is whether U plus V is going to be in W for all U and V in W, and whether C times U is going to be in W for every scalar in our field and for every vector U and W. Now what this first property means is sometimes you see that summarized to say that W is closed under addition. So if we take two elements, we add them together, and that new element is in W, then it's closed under addition. The second property, where we just take a vector and we multiply it by a scalar, and if that product is also in W, then we say that W is closed under scalar multiplication. And so what this theorem lets us do is to say that a subset is going to be a subspace if it's closed under addition and closed under vector addition, and it's closed under scalar multiplication. So what does the proof look like for that? Well, if we suppose that 1 and 2 hold, then what that means is that we really do have these operations of W cross W into W, where we take two vectors and we add them together. And it also means that we've got this scalar multiplication operation that's defined, that if we take a scalar and a vector and we multiply those together, that ends up in W as well. And so those two properties show that we do that these vector addition and scalar multiplication are well defined, that the image actually is in W. And because these guys already satisfy all of the properties from V, we know that those operations are the same. They satisfy the properties in V, then they also are going to satisfy the properties already in W, and therefore W is going to be a vector space. Now, if we flip that around and say that W is going to be a subspace already, then W is a vector space. And so it is closed under vector addition, and it is closed under scalar multiplication. And so properties 1 and 2 hold already. And so that kind of gives us a way of seeing that, kind of a quick and easy way of seeing whether two vectors or whether a set of vectors will actually be a subspace or not. And so kind of two important sets that we've talked about before and are going to come up again over and over and over. If somebody gives us a linear transformation from a vector space V to a vector space W, then remember that we defined the kernel of T to be the set of vectors in V that get mapped to 0. And that the image of T is going to be the set of vectors in W such that there's some vector V in V for which T of V is going to be equal to W. And so that these are subspaces of V and W respectively, we'll leave that as an exercise for your homework. Kind of another example that we can take from this is that if somebody's given us the vector space R3, and if we define this set of V1, V2, 0, the set of vectors that are of that form, then I claim that this set V is going to be a subspace of R3. All right. Well, our first step is to see that V is not empty. Well, 0, 0, 0 is the 0 vector is in V, so it's not empty. Then if we take two vectors that already have that form, V1, V2, 0, U1, U2, 0, Then if we add those together, we get V1 plus U1 for the first component, V2 plus U2 for the second component, and 0 for the third component, 0 plus 0. And so since our real numbers are closed under addition, it means that this set V is also going to be closed under addition, under vector addition. And likewise, if we take a scalar c that's a real number, and we multiply c times one of the vectors of this form, then we get c times v1, c times v2, and c times 0. But that just gives us cv1, cv2, and 0. And so that does meet our definition of being in V. And since R is closed under multiplication, that's why those are elements of V. And so the theorem that we just did says that this subset V is actually a subspace of R3. And I mean, we probably recognize that pretty readily as being, this is just your xy plane. You're imagining your xy plane embedded in three-dimensional space. We could likewise have planes, the xz plane, where the y component was 0, and we could have the yz plane, where our x component was 0. So it's not terribly surprising that there are three kind of immediate examples of a subspace. So this is probably a pretty good place to stop for this video, and so stay tuned for the next one where we kind of continue our discussion of subspaces. I will see you guys then.